All right, we'll continue. Okay, so where we left was part 2. We want to argue that if you have any d plus 2 points where the data set is in d dimensions, so x0 to xd plus 1 are vectors in rd plus 1, then they cannot be shattered by h. Okay. Now the argument of just counting equations and unknowns does not work because of the non-linearity in the decision rule. So we need a more sophisticated argument. And we will do the following. We want to argue that there will always be some choice of y1 to yn which cannot be satisfied by any w regardless of how x1 to xn is selected. So if you go back and recall our discussion for d equals 2, we had 4 points, right? There was x1, there was x2, x3, and x4. There were 4 points like this. And we said that regardless of how you place them, there will be 2 labels, the plus minus sequence, for example, which cannot be achieved by any weight vector. So no matter how you draw the line, there will be some sequence of y1 to yn, in this case y1 to y4, which cannot be satisfied. And so we want to formally prove this observation. Okay? Now, of course, if we had yi equals w transpose xi, if that was our decision rule, it was easy, just count equations and unknowns. But the challenge is the non-linearity of the sign function, which is what makes this proof difficult. So the way we will do it is by making the following observation. Since these vectors lie in d plus 1 dimensional space, and there are d plus 2 of them, they cannot be all linearly independent. Right? They have to be linearly dependent because you have more vectors than the dimension of your space. Okay? So since x0, x1 to xd plus 1 are linearly dependent, you can always write one as a linear combination of the others. Let x0 be written as a1 x1 plus a2 x2 plus a3 x3 all the way up to ad plus 1 xd plus 1. So here x0 is non-zero. All the vectors are non-zero because we have a bias term as the first term. We have a 1 as the first coordinate, so x0 is non-zero. And at least one of the ai is non-zero for some I. Because the left-hand side is non-zero, the right-hand side cannot be 0. So one of the coefficients is non-zero, right? That much we know.
x1 to xd plus 1, right?
So these are d plus 2 vectors.
Or g plus p.
Okay, so we can write it in this form. And now we have to propose a choice of labels that cannot be satisfied by any w. And this requires a bit of an art. You have to think about the problem and come up with this labeling. So we claim that the following choice of W or the following choice of labels y0 to yn cannot be satisfied by any W. So in the case of 4 points, we proposed one choice of labels, right? And it was clear that choice cannot be satisfied by any line. We want to do this now in the general case. We want to propose a choice of labels that no matter what weight vector you select, you won't be able to satisfy. So the way this is done is like this. For I equals 1, 2, up to n, we let yi to be plus 1 if ai is positive or equal to 0. And it is minus 1 if ai is less than 0. So a1 to a, so n is d plus 1. So for I going from 1 to d plus 1, we want to define the label of each of the data vectors, right? x1 has a label y1. I will set y1 to be plus 1 if the coefficient in this expansion here is positive or 0. And I will set it to be minus 1 if this coefficient is negative. Okay. For the second vector, I have to define y2. y2 will be set to 1 if the coefficient here in this expansion is positive or 0. And it will be set to minus 1 if this a2 is negative. Is that clear? So how do I get a1 to ad plus 1? It comes from my data set, right? I'm able to write x0 because these vectors are linearly dependent. There exists a choice of a1, a2, a3 up to ad plus 1 such that this condition holds. So given x0, x1, x2 up to xd plus 1, I can now find what a1, a2 up to ad plus 1 are because this expansion, through this expansion. I can write 1 as a linear combination of the others, and that's where these coefficients come up. Once I have the coefficients, I can define the label in this way. For each of these ones, I will select the label to be plus 1 for that point if this coefficient is positive, and minus 1 if it is negative. And if it is 0, I will just arbitrarily set it to 1.
And you're saying that if we choose the labels this way, then we won't be able to...
Then you cannot shatter. That label cannot be realized no matter how you select W. That is the claim. And I had to also specify what y0 is. So I will always set y0 to be minus 1. So the label for the first point will be minus 1. And the labels for all the other points will be chosen using this relation. If the coefficient is positive, the label is plus. If the coefficient is negative, the label is minus. And the claim is that this sequence of y0 to yn cannot be satisfied no matter what weight vector w you select. That is our claim. Okay? Can anyone see why? Can anyone see how we get a contradiction? Let's say I select yi's according to these labels. So this can always be done. I can select y1, y2 based on this formula. Then the claim is you can never have y0 to be minus 1. Y0 will always be plus 1. Why is that? Anyone see?
You multiply that expression by WT.
Uh-huh.
And then sign everything.
Exactly. So if you take, so the claim is no matter how you select W, this label, you can always, will be forced to set the label of x0 to be plus 1. It will never be minus 1. To see that, well, what is y0? Y0 should be the sign of W transpose x0. That's what y0 is by definition, right? Y0 has, based on our decision rule, W transpose x, if W is our classification boundary, the weight for the classification boundary, the true label should be sine of W transpose X0. But now X0 has this expansion, X0 equals this. And so if the way we have selected these labels, if we multiply by W transpose on the right hand side, each of these terms is forced to be positive. The way this construction works is that each of these terms, when we multiply by W transpose, A1 transpose W transpose X1 will be positive if it matches this label. A2 times W transpose X2 will be positive, and so on. So all these terms will be positive. So the right hand side will be forced to be positive. You cannot set y0 to be -1. That is the argument. Let's see that more carefully. So if we look at y0 hat, this is the sign of W transpose X0. And we want the left hand side to equal -1 because that is what we want, what we suggested the label to be. But what is X0? X0 is A1 times X1 plus A2 times X2 up to AD plus 1 times XD plus 1. Right? So let's multiply by W transpose on both sides. Now, W must simultaneously satisfy the label for X1, the label for X2, and the label for X3, and so on. The same weight vector should satisfy all the labels if it is going to work. Right? Let's say it satisfies the label for X1. Then the claim is that this term should be positive. Our claim is that this term should be positive if Y1 is the sign of W transpose X1. Why is that?
Because W transpose X1 will be 1.
Because W transpose, so if Y1 is +1, then W transpose X1 will be +1.
And A1 will be 1.
Then Y1 is selected so that it is a sign of A1. If A1 is positive, Y1 will be +1. And hence W transpose X1 will be positive. If A1 is negative, then W transpose X1 will have a sign of -1. So W transpose X1 will also be negative. So A1 times W transpose X1 should always be positive. Right? So we have two cases. Either A1 is positive or A1 is negative. If A1 is positive, then Y1 is the label is +1. If A1 is negative, the label is -1. Now Y1 should equal the sign of W transpose X1. So the point is that when A1 is positive, the sign of W transpose X1 will be +1, which means W transpose X1 will be positive. So the product will be A1, which is positive, times W transpose X1, which is positive. So the overall product will be positive. If A1 is negative, then W transpose X1 has to be negative to satisfy this label. So this term is always positive, regardless of whether A1 is positive or A1 is negative. And the same argument can be made for every term. This term is positive, this term is positive, and this term is positive, right? For if we are going to satisfy the labels associated with Y1, Y2 to YD, our construction is such that each of these terms is guaranteed to be positive. So W transpose X0 hence will be positive. But we chose the label to be -1, so that's a contradiction. So this means that the right hand side is positive and you get a contradiction. Okay, so the proof is a bit abstract. Typically finding VC dimension for like general models is a hard problem. But the good news is that people often do it. In literature, people publish research papers where they give bounds on VC dimension. Once you have the bounds, then things are easy because now you can apply them in the generalization bounds. You know what is the right size of the data set to use and so on. But for the first time, computing the VC dimension for any model typically requires a fair bit of mathematical machinery because you have to like prove two parts, the achievability and the converse. Find the breakpoint and find the largest size of number of points you can shatter, right? These things are not easy. So these are usually research problems. So the takeaway is that in D dimensions, the VC dimension, and if H is linear classifier, then the VC dimension of H is D plus 1. It's exactly the number of free parameters you have in your weight vector, the bias term plus the D terms, one for each of the D coordinates. So this is what we have established. The VC dimension of a linear classifier in D dimensions is D plus 1. So I'll ask any questions about the proof. What we did on the, anything not clear on the previous page. I'll go back again. Do people see how the contradiction follows? Because you will have to find some VC dimensions in your homework this week in the tutorials. You'll get practice on finding VC dimensions. So this is, you're responsible for this part. This is not optional. Is everyone okay with this? I don't see any reaction, so I don't know what happened. If people just decided to stop listening, or this was clear.
At the start, why did we choose y0 equals -1?
The idea is we want to provide a sequence of labels for which no weight vector will work. You will always have some label that is misclassified. So what we did was we selected, we have D plus 2 points in total, right? For this D plus 1 points, we selected the labels in this fashion. And for the last, so I say that if I have a weight vector that satisfies this D plus 1 points with the labels chosen in this fashion, then it will never be able to satisfy y0 to be -1. It will be forced to put a label of +1 on the point x0. So my points are x0, x1, x2 up to xd plus 1. So I want to now assign a label to each of these points, all the d plus 2 points. What I'm saying is if I choose the labels of these d plus 1 points in a careful way, in this particular fashion, and if I force my weight vector to satisfy all these labels for these d plus 1 points, I will always be forced to select the label of this to be +1. It can never be -1. So
it wouldn't work for when you flip the signs.
Yeah, so if you flip this to -1, then it will never work. So that's why we chose to get a contradiction. We showed that this, to make this -1, you will fail.
You chose A based on what the sign of A, like omega transpose x1, right? You didn't choose the other one.
So how are A1, A2 chosen?
So A1, A2 are chosen based on what the sign of omega transpose x1. Like if A1 is chosen based on omega transpose x1.
No. Like I am given any points x0 to xd plus 1. I don't look at the labels. A1, A2 come from the geometry, right? Because I can write x0 as some linear combination of the remaining points. So x1, x2 points, we know that there was one, so we fixed these 4 points. And now we said that if you have plus, minus, there cannot be any linear classifier that separates them. We want to generalize this to arbitrary case. So I'm proposing this choice of labels. I'm going to look at A1. If A1 is positive, I set the label to be +1. If A1 is negative, I set the label to be -1. Then I go to A2 and I do the same. I look at the sign of A2. And I do this for each of those D+1 points. Okay? And so this is now a function of all the A's and the X's. So once I fix my labels in this way, I still have to specify the label for the first point. And I always set to -1. And I claim that no matter how you select W, this sequence of labels cannot be satisfied by any weight vector. So this is the generalization of the plus minus example we had here. Right? So I have to do it in the arbitrary case. So it has to be implicit. It cannot be very explicit like this. And so this was the choice which leads to contradiction. And the contradiction then comes on the next page. What we say is that based on this label, if W satisfies the label for x1, the label for x2, the label for x3, the right-hand side has to always be positive. It can never be negative because of the argument we made here. Where hence the left-hand side has to be positive, so you can never get a minus label. That's the flow. Okay, so I'll let you absorb it. You will do some problems on VC dimensions in this tutorial. So make sure you go and follow it. This is the hard part of the course. So now the idea is you can extend this. We were discussing linear models, right? What if you have a non-linear model? Consider a second order model. So imagine that your data, you are in 2 dimensions originally. And so if you take y to be sine of W transpose X, what will be the VC dimension for this model? We just did this. This is in 2D is 2 here. So what's the VC dimension? 3. Okay. But now let's say that I want to do a second order model, not this one. So I consider a transformation 1, x1, x2, x1, x2, x1 square, x2 square. And I do y hat is sine of W transpose X. What's the VC dimension of this model, or W transpose Z, sorry. Well, Z again, now look at the dimensional. This is again linear in the Z space. So the VC dimension of this is just the size of Z plus 1. So here you have the size of W. W is now a vector in 6 dimensions. 1, 2, 3, 4, 5, 6. And so the VC dimension here is going to be 6. So if you had 30 data points, you can only use this model to make sure overfitting does not happen, because of our rule that the number of points should be 10 times the VC dimension. If you were to use this a second order fit, you should have at least 60 points. Otherwise, this model may be risky to use. You may end up overfitting, right? So this says that there is some intuition as to how complex a model you can select, what order polynomial to fit in based on the VC dimension. As you go to higher and higher order polynomials, the VC dimension will quickly start increasing because you will have more and more terms in this particular expansion. And so you will have to have correspondingly more points in order to fit. So for example, if you go to 10th order, you can do a quick calculation and see that you will need over millions of points in order to make sure that the generalization error is small.
If it wasn't, so this is linear in terms of W, right?
This is
This,
linear.
this is, if it was non-linear in terms of W, then this wouldn't be applicable. The D plus 1 we see then.
Right. So this is a linear model for W in the Z space.
Yeah.
There is a little bit of subtlety in that these elements are not independent.
Yeah.
There are just 3 parameters of x1, x2 for which, but you are expanding them here. So the question is, will you still shatter all 6 points because they cannot be arbitrarily placed.
Yeah.
They have to be placed subject to this curve here, right? This is some manifold as such. The thing is, it still works out. Like it does not constrain. You can still shatter. We can show you can shatter any set of 6 points even with this classifier, and 7 or more points constitute a breakpoint. I think basically if your data vector belongs to Rd and you have mth order polynomial, then the VC dimension can be shown to be m plus d choose d, which is of the order of m to the d. It's possible to show this. So it increases exponentially in the dimensions, or it increases exponentially in d here, and it increases m to the d. And we'll discuss that in the tutorial. Okay. So this is all we have for VC dimension. Now when you talk about, say, regression problems, so let's say we are interested in linear regression. Okay. Then again we have the training error. And the test error. Okay. So, and we want to find a relationship between E in and E out. The test error, and we want to say if the training error is small, the test error should be small, and so on. Now, it turns out that the theory of VC dimension is not that useful for regression problems. This is because if you even think of how dichotomy was defined, it's 2 to n, 2 to the n. If you look at the number of distinct values the labels can take, in the binary case it takes 2 values and then it raises it to the power of n. So things like the dichotomy set, the growth functions have been carefully chosen so that they can be defined well for the classification setting. But if your labels are real valued, then those definitions do not generalize. In this case, so the VC dimension approach is not suitable. But the rule of thumb still works. So now the rule of thumb that we had, which is that n, the number of training points, should be of the order of 10 times the dimension or the number of free variables. So if you are in, say, linear regression, then it's the dimension in which you are operating. Otherwise, it's the number of free variables in your weight vector. This is still applicable. But a more systematic way of analyzing this is through another technique called the Bias-Variance Tradeoff. So the way typically we understand overfitting in regression problems is through a different tool called the Bias-Variance Tradeoff. And so we'll start discussing this next lecture. Okay, so we'll stop today here, and starting next lecture we will discuss these quantities in the context of regression.